All right, lesson 2, planar graphs and Euler's formula. So for those of you that did year 11 general, you hopefully remember a little bit about this. Again, going to be quite a few definitions in this one. Make sure these are all written down somewhere in your notes because you never know what kind of questions you're going to get. All right, so one little definition you might not have seen before is what's called a degenerate graph. It's simply just a graph with no edges, so it's purely made of vertices. You don't really typically deal with these too much. However, if you do get a question in a SAC or exam situation where you're asked to define it, it's important to have that in your notes. So it's a graph or a network that contains no edges. All right, one that you would have seen before is that called a complete graph. Where every single vertex in your graph or network is connected directly with just one edge to every other vertex in your graph or network. So I'll draw up an example of that one. Alright, so I have 4 vertices. If all my vertices are connected directly just with one edge, then my complete graph will look something like that. So no matter which vertex I'm at, I can get directly to every other vertex via just one edge. Sometimes you'll get a question which will say something like, if you have a complete graph with 6 vertices, how many edges will there be? And we have a little bit of a formula for that. So that looks something like this. So the number of edges is equal to whatever the vertices are, multiplied by the vertices again, minus 1, all divided by 2. So just with this one we could easily count the number of edges, but if you get one that says 10 vertices or 20 vertices, what you can do is just use this little nifty formula. So the edges, in this case, it has 4 vertices. Oops. 4 take 1 is 3. So 4 take 1 is 3, have mind blank for a second there. 3 times 4 is 12. 12 divided by 2 is 6. Yeah, I got 6 edges in there. So just a nice little formula if for whatever reason you need to calculate the number of edges in a complete graph. So that brings us to planar graphs. Alright, planar graph has no intersecting edges. So there's no edges crossing over, they are just all non-intersecting. So at the moment this is not drawn as planar because there are edges crossing over. It could be redrawn as planar, which we'll look at in a moment. But at the moment it's not planar because there are edges crossing over. We don't want that when it comes to a planar graph. So we've looked at vertices and edges. Another thing we need to look at is what's called the regions or the faces. So the regions / faces, they're the enclosed spaces inside of a planar graph. notice with this one, I've just drawn the letters next to it. That's fine. Sometimes you get situations where it looks like that. So at the moment, this is a planar graph. There are no edges that intersect or cross over each other. We have 4 vertices, A, B, C, D. We have 1, 2, 3, 4, 5, 6 edges. Now the other new concept we're looking at is the faces. So they're the enclosed spaces. So that's a face, we'll call it face 1, phase 2, or region, depending on the resource you're looking at. Phase 3. Now, for those of you that did year 11 last year, you might remember that the infinite space around the outside of our graph network also constitutes a face. So in this case, outside there is phase 4, or the 4th phase of our graph network. So don't forget about that space that encloses our graph network. That also counts as a face. Now, a lot of the time we can also write or redraw our graphs and networks as a planar. So sometimes, let's have a look at another example. We might be given a graph that looks like this, so really similar to our first one. So it's got 5 vertices. Alright, so at the moment, that is not drawn as planar. What we can see is we have an intersecting edge in the middle there, therefore we can't count as planar. However, we can simply redraw this. Now we can move the vertices around as much as we want. When we're redrawing graphs, it doesn't matter really about their location. The important thing is the connection between the vertices. So if I was to redraw this, I have to maintain all those same connections. So A must always be connected to B, C, and E. If I was to redraw it and I didn't redraw those connections, it's not the same graph. It's completely different. But I can shift the vertices around as much as I want, as long as the connections remain the same. So I'm going to redraw this as planar. There's many different ways that can be done. There's no one right way, as long as I keep those connections. So I've gone around the outside like I did before. I'm going to go from A to C again, but then that connection from B to E, I can't go through because then it won't be planar. So I can just go right around. Doesn't matter how I do it. I can go the other way, whatever, it doesn't matter, as long as those connections maintain. So that's redrawing a graph into planar form. Okay, this finally brings me to Euler's formula. So again, those of you that did year 11 general will hopefully remember this. Euler, one or the other. So what this is a relationship between the number of vertices, edges, and faces in a planar graph. All right, so remember, this is just for planar graphs that we've looked at. Well, what color? Let's go with purple. All right, it can also be written many ways depending on what we're solving for. It can be transposed. One way it can be written is V minus E plus F equals 2. So vertices, edges, and faces. This just shows one way to write out the formula. As I said, you can transpose it as much as you want, so you can take the F over there, or you can add the E over here, whatever. It doesn't matter, but this is essentially what it will look like. So for any planar graph, this rule works. The number of vertices minus the number of edges plus the faces always will equal 2. Let's just quickly prove that, and we'll make sure it works for this one we did here. So up here, what we had was 5 vertices. We had 1, 2, 3, 4, 5, 6, 7 edges. We had 1, 2, 3, 4 faces. 5 minus 7 is -2, plus 4 equals 2. So in that case, it worked. A lot of these questions that you'll get around this, you'll be required to find or calculate the number of vertices, edges, or faces based off some other information. So what I mean by that is, as an example, a planar graph has, let's go, 6 vertices and 11 edges. Calculate the number of faces. Oh, I'm running out of room. And what we can do is we can just use Euler's formula to calculate that. So we know that V is equal to 6 and E is equal to 11. We're trying to calculate F. So let's put that into our formula. Vertices, which is 6, minus the number of edges, 11, plus F is equal to 2. Then it's just a little bit of algebra to solve for that. You can solve it in your CAS if you really want to, or if you're feeling confident with your algebra, you can also just do it that way. So 6 minus 11, I'll do that first, is -5. Add 5 to both sides, I get 7 faces. Therefore, if I have a planar graph with 6 vertices and 11 edges, it's going to have 7 faces. So that's how we can apply Euler's formula to calculate for those unknown values. That's 9.3. Make sure you're asking your teacher if you need any extra help or additional clarification with any of that stuff. Thanks, guys.